Welcome students. My name is Nebojsa Nakicenovic. I am the Deputy Director of the International Institute for Applied Systems Analysis in Austria, and I'm also Professor of Energy Economics at the Vienna University of Technology in Austria. I would like to welcome you to lecture number 5. It deals with technological and economic feasibility of the transformation. To a large extent, and primarily, it is based on the flagship report of the German Advisory Council on Global Change. It is based on the flagship report that's entitled World in Transition, a Social Contract for Sustainability. This lecture consists of 2 episodes. I will present to you the first episode on global energy transformations. I will deal with issues such as historical dynamics of development, possible future pathways of energy and other developments, and what might be the investment needs and how to finance them. And then my colleague, Professor Jürgen Schmidt, will present to you episode 2 that will also deal with global energy transformation, but will focus more on the challenges and possible solutions. And at the end, we will have the interview. Let me first start by showing to you what might be some of the learning outcomes that I hope are possible from this lecture. Number 1, I hope that you will gain a better understanding of the historical evolution and transformational change in the energy systems, improve perceptions of the major energy challenges in the world, such as the lack of access, improvement of security, and environmental compatibility at all scales. I will also address the question of what is the availability of fossil energy resources and how large are the renewable energy potentials in the world. Thereafter, I will show you a range of technological options for transforming energy systems at all scales, from local to global. What are the investment requirements today and what might be the future ones for transforming energy systems? And last but not least, the many potential co-benefits of energy transformation, including economic development, improved security, and environmental protection at all scales. So that is basically the plan for this episode number 1. And let me start immediately with the substance of the lecture. The lecture is about transformation of energy systems, and I would like to show you a kind of a bird's eye view of the grand transformation that has taken place in the evolution of the humanity on this planet. Please note that on this graphic, the vertical scale is shown in the logarithmics, on the logarithmic axis. We start with 1 million, 10 to the 6, go to 10 million, that's 10 to the 7, 100 million, 1 billion, and then 10 billions. On the horizontal scale, you have time before the present, again, starting at million years before today and going to the present. If you look back into the history, the first social order were the hunters and gatherers that did make some tools out of stones, wood, and animal bones. At that time, as you can see on the graphic, the global population was very small, maybe 6 million people on the world. But about 10 to 5,000 years ago occurred a major revolution in the human society. It is called Neolithic Revolution because it led to the agriculture, to the establishment of settlements, of city-states, the domestication of animals. Animal muscle power was used to replace human muscle power, and that expanded greatly the niche of humanity on the planet, but has also changed the planet. It led to deforestation and so on. And over the 5,000 to 10,000 years that this revolution lasted, global population increased exponentially to about 1 billion people about 200 to 300 years ago. And the last revolution was the so-called Industrial Revolution over the last 200 years that was really explosive, leading to human population growth to 7 billion people to today, and has changed the nature of our societies and is influencing many planetary processes. So the major thesis or the vision of this lecture is that we are on the brink of another grand revolution or major transformation in human society over the next decades. We expect that the world population would peak at about 9 billion in about 2050, about 40 years from now, and possibly decline thereafter. So the question is, what are the challenges of this transformation and how it might occur? Now, in the flagship report of the German Advisory Council on Global Change, we have provided a vision of how this might occur, what are the drivers of this grand transformation. And our view is that the proxy or a way to symbolize this transformation would be to say that we need to decarbonize the world, to reduce the amount of carbon in the energy, and that's synonym for dematerialization, and many other dimensions of improving the efficiency and being more compatible with the global planetary constraints. The good news is that this transformation is already taking place. There are a growing number of actors of change. I'm giving you here only a few examples. Green businesses, green cities, many initiatives in the area of the social society, civil society. Science is providing a huge new body of knowledge for precautionary principles. And many international and national government institutions, such as UN, are also taking many initiatives. All of that is leading to the fact that the legitimacy of the business as usual, illustrated here as BAO, is eroding, and this green curve, S-shaped curve, illustrates a transformation toward the vision of a low-carbon society for which we have many studies and many narratives. And that is the focus of this presentation today. Now, we can learn from the past. We don't have to go to these grand transformations of the Neolithic and Industrial Revolution. In the more recent history, there are many examples where a vision of a better future based on normative perspectives has led to a major societal changes. I would flag here the abolition of slavery, increase of democracy in the world. Today, about 50% of the global population lives under democratic rule. European Union, United States, many of these new structures of government represent such visions as well. Often, a major transformation occurs also because the current system, business as usual, is in a crisis and its legitimacy is eroding. Professor Schumpeter has called it the gales of great creative destruction. If you think of the Great Depression in the 30s, that has led to new structures. Structural adjustment projects today will also establish new systems. These are also drivers of change. Crisis of the financial system and the economic depression over the recent years might have the same effect. So there are things that are going on that indicate that such a revolution is possible. Technology gives many examples where the rapid innovation diffusion has caused major changes. Think of the replacement of horse carriages by the automobiles, or the information and communication revolution that is still going on. Last but not least, let me highlight fundamental changes in knowledge that provide for transformational change. Much of that knowledge is research-driven and increasingly based on the precautionary principle that we look forward and try to anticipate the problems and not be surprised by them. The protection of the ozone layer is one such example that worked really well, and there are many initiatives today to do something similar in the area of climate change mitigation. What are some of the characteristics of the energy transformation itself? Well, we are currently on a very carbon-intensive development path with ever-increasing emissions of carbon dioxide and other greenhouse gases. And yet, if we want to be consistent with the precautionary principle, it is necessary to stabilize temperature change at a level that's not dangerous. 2 degrees is a good compromise for stabilization, but to do that, we would need a major trend reversal in these emissions by 2020, and that means that the global energy system that is today predominantly based on fossil fuels, they constitute about 80% of global energy, would have to be transformed away from the fossils toward decarbonization. And in parallel to that, the second transformation that needs to occur is that almost half of the global population, 3 billion people in the world, lack access to modern forms of energy. That means they do not have good access to electricity and have to cook with solid fuels. That leads to many environmental problems, including major burden of diseases. It is estimated that about 2 million people in the world die prematurely because they cook with solid fuels. Let me show you here in this graphic an illustration of where the people live who do not have the access The graphic looks a little bit complicated, but if you look in the lower left corner, you can see the color code. As you go from green to red, the number of people who have access to electricity decreases. So the bright red are the people who do not have the access to electricity at all. That's about 1.5 billion. And as colors intensify for pale to strong, these are the people who do not have access to modern cooking fuels and have to cook with the solid fuels. If you look at the red regions, Nepal, Indian subcontinent, the people who live there predominantly cook with solid fuels, biomass, but also do not have access to electricity. In China, access has improved quite a lot, but still many people cook with solid fuels, primarily by coal. Sub-Saharan Africa is a challenge of its own. Very, very sporadic access in urban areas and predominant cooking with the solid fuels, traditional biomass. So that's the nature of the challenge. So if you look at the planet in about 20, 30 years, the idea would be that everybody would have the access and that this color scheme would disappear. Now, a question that might be asked is, if we connect the 3 billion who do not have the access and the population growth, is it possible? Do we have enough energy? And I would like to reframe this slightly differently. What I would like to show you here in proportional scale is, rather than talk about energy units, I'll be talking about carbon dioxide emissions that would result if we would burn all of the fossil energy that's available to us. So look at the two squares there in the middle of the graphic. On the left is the conventional reserves of natural gas, and on the right, on your right, is conventional reserves of oil, expressed in gigatons carbon dioxide emissions or billion tons of carbon emissions. Now, these are the reserves that can be extracted with current technology, with current economics, and with the current geological knowledge. To put it in practical terms, natural gas would last about 70 years at present level of consumption, oil roughly 40 years. And if I sum those two figures, we are talking about potential emissions of 1,000 to 1,500 billion tons carbon dioxide. Now, that in itself probably doesn't mean much to you, but let me try to put this in a proportion. The historical emissions are the same magnitude. So the whole Industrial Revolution was powered by the same amount of emissions. About 1,500 billion tons of carbon dioxide have been emitted. Let me further put that in the proportion. About half of that amount has actually stayed in the atmosphere. About 750 billion tons of carbon have remained in the atmosphere. The rest has been washed out and deposited in the new growth of biomass, but primarily in the oceans. The current content of the atmosphere is about 3,000 billion tons. So you can see that if we would burn all of the current fossil reserves of oil and gas, we would be adding on the order of 750 billion tons of carbon to the atmosphere, and that is estimated to be the maximum what we can do if we want to stay within the constraint of 2 degrees. The less, the better. Now, but this is not the end of the story. Coincidentally, the biomass above the ground contains just about the same amount of carbon. Clearly, we cannot afford to burn that. But a small portion could be used sustainably in the transformation toward renewable energy sources. In comparison, I would like to show you that coal is a huge resource. So that's both a curse and a benefit to the countries that do have large coal reserves, such as India, China, United States, and Australia, or Russia. But I would argue that it cannot be used without capturing carbon, and probably only a small part can be used. And one of the largest resources that we have today that's being increasingly talked about is so-called shale gas. That's unconventional gas. Huge amount of carbon is locked into that. But this is a resource that's already being commercially extracted in the United States. There are many environmental concerns, but also in many countries' activities to further push the frontier and tap into this large resource of natural gas. And on your far right, I've added also unconventional oil. These are primarily tar sands, very difficult, similar to coal. And last but not least, let me just show you that there is another unconventional form of fossil energy natural gas locked in ice, so-called gas hydrates. This is a huge resource and might be larger than everything you see here on the graph. Many of you have not heard about hydrates, so let me show you how they look like. This is a core bored from the bottom of the ocean. They're prevalent at the bottom of the ocean, but also in the permafrost regions. And in fact, this is one of the scary climate stories. If the Earth warms, much of this methane might be ending up natural gas in the atmosphere, and that's a very strong greenhouse gas. So you can see that fossils present many, many challenges. Now, how can we move away from fossils? Well, the good news is that renewables are also plentiful, not just the fossil energy sources. And I would like to illustrate to you on this graph in perhaps a bit unconventional manner. As you all know, Europe has very high population density and relatively high level of energy consumption associated with high degrees of affluence. And all of the areas in Europe that are marked in orange or yellow represent places where you cannot generate the amount of energy locally needed for the current demand. So these are substantial urban areas around Europe. On the other hand, if you look at the squares that are colored blue to white, these are the areas where sunlight and wind can generate more energy per square meter than it's demanded. So it could be anywhere between a quarter or a third of the energy in Europe could be generated locally on site. And this is a huge opportunity throughout the world, in particular in Asia and even more so in sub-Saharan Africa. But that is not all. We have also large resources of renewable energy sources that would be associated with infrastructures and big capital investment. This is the idea of producing energy in the deserts. I'm showing you here Sahara, and you can see that the square of about 300 times 300 kilometers, relatively large area. For example, almost as large as the country where I live in Austria. But if we would build solar power plants, we could produce all of the global electricity, showing to you how large the renewable potentials are. And there are many schemes for tapping in those potentials. This is a particular one that I like. You can see here North Africa going down to Sahara and Sahel region toward the bottom of the graph. This is the idea of generating solar energy. Building a network for electricity, transport, and water all the way down to Sahel, where people are suffering from lack of water. It's a very arid area, and that's inhibiting economic development. So I think this is a great vision of how we could achieve development in North Africa, something where Europe might consider investing in. I think much of these programs would be lucrative if one has a long-term view. But one can go further. Once that system is built, one could imagine that also this could go to Europe. This is the idea of desert tech that has been popularized quite a lot in recent years. So you can see that we could have a combination in Europe and throughout the world of on-site, small-scale generation combined with large-scale renewable energy systems. This is not only limited to Europe. Let me show you a vision for Asia, where energy demand is growing very rapidly and is very, very high. Here on the left, on your left, you can see solar panels producing electricity. That electricity would be transported by so-called supergrid through the urban areas of Asia, China, via Korea, even to Japan. And think if a system like that existed today, how much easier would have been the aftermath of the Fukushima disaster in Japan. Right now, Japan is not connected to the mainland Asia in terms of energy. There is no Asian grid. And the little insert here on the right shows you how such a supergrid might look like. There is a pipeline that would be transporting renewable methane or renewable natural gas, or perhaps hydrogen at very low temperature. That would also cool the superconducting cable that you see in the middle. Next to it is also another pipeline for trains, in this case magnetic levitation trains. In Japan, plans have been announced to build such a system between Osaka and Tokyo. So this is a large infrastructure vision, and we will probably need both local and large scale for the urban areas, because already today 50% of the population in the world lives in the cities. But this is not just a question of supply. At the end use, we also have to make huge efforts. Buildings generate major demand for energy. About 40% of global energy is required for the buildings. Here you can see on this graph two pictures that illustrate the situation in Europe. On the left is a traditional building, let's say built in the 60s, without much concern for energy efficiency, with relatively high requirement of energy per square meter. And on your right, you can see an alternative retrofitted house, which might reduce up to 90% the energy needs. But somebody might say, well, okay, this is not economic, but even if we reduce 50%, we would be halving the energy requirements for the buildings. And that's a huge leap forward. On top of that, today we can build passive new buildings that need absolutely no energy and can produce energy on site. So this is a major revolution, and it's clear that this is not just a technical issue. We also have to find ways of how to adjust our lifestyles and behavior to be compatible with these new technologies. And the challenge is huge in the area of transport system. So it's not just a question of electric mobility and having more efficient cars. It's also a question of going from from private to public transport to collective transport systems such as rail and buses that could also radically cut down another major energy demand. This is mobility. So let me try to summarize what are some of the framework conditions for going forward. I would say we have two major challenges that I've tried to illustrate. One is to achieve universal access for the 3 billion people who cook with solid fuels. The other one is to decarbonize global energy over the next 30 to 40 years by the middle of the century. What are the preconditions? The precondition is that energy demand should not increase. That is possible to drastic energy efficiency improvements that would also lead to major reductions of carbon dioxide and greenhouse gas emissions. But I would also like to stress, and that is in our flagship report that's highlighted, that this is not just a question of technologies and institutions, it's also a question of behavior and lifestyle changes. So we really have to transform our societies. And I've mentioned at the beginning that we see some of these agents of change. Change is already going on. I think symbolically that's signified by the fact that the UN General Assembly has declared the year 2012 to be the year of the sustainable energy for all. And even more than that, the UN Secretary General, Ban Ki-moon, has put his political weight behind the idea of achieving 3 aspirational and very ambitious goals that are achievable. And I think that the WBGU flagship report presents how one could achieve that. Number 1 goal that I already talked about is universal access. Number 2 is double the efficiency improvement of energy in the world. And number 3 is double the renewable share from 15% today to about 30%. So these 3 goals are very important. The flagship report shows how they might be achieved, and let me try to illustrate that to you, how that might look like. The first picture shows you the evolution of the global energy in the world to today during the Industrial Revolution. Some of the key technologies are depicted on that graph. On the bottom are stacked the fossils, coal, oil, and gas. You can see that they've grown exponentially at about 2% per year. The green curve shows the biomass. Originally, we all depended on traditional biomass. Its contribution stayed about constant. Now we are slowly shifting to modern biomass. On top, you see in blue hydropower, and in yellow, the contribution of nuclear. The modern renewables, such as wind and solar, are hardly discernible. They're still a very small share of the total primary energy. But that needs to change. And I would like to show you a vision how this might change. Number 1, on top, the gray area, if you can see, shows that the role of savings is huge. So that's number 1. Efficiency avoids energy demand, and that is the key. In this kind of vision of the future development, we would have 40% reduction compared to a business as usual. Then the role of renewables would be significant, increasing to about 30%, doubling, consistent with the goals of Ban Ki-moon. On top of it, below, you can see that the role of fossils would significantly decline over time. In this case, nuclear continues making a contribution, but I will show you a case also that we can do it without the nuclear, so there are degrees of freedom in here. In this case, the intermittent nature of renewables requires also storage that harmonizes well with natural gas, which is a virtual storage. When there is no sun or where there is no wind, one can use gas power plants to produce electricity intermittently. And what's significant is we do have a peak of oil, despite the fact that we have not squeezed the last drop of oil from the planet. This is required because of the transformation to improve the efficiency in homes, to improve the efficiency of vehicles. Now, in this kind of future, we might need to have some carbon capture and storage. This is yet another problematic technology, but if we don't trap the emissions enough, if we rely on fossils too much, we would have to remove the carbon. And another possibility would be to remove carbon from sustainable biomass, de facto generating negative emissions because biomass absorbs carbon dioxide when it grows. Now, let me show you a possible vision without nuclear. You can see that renewables here have even a more important role. Nuclear moratorium occurs in the world, indicating that we do have degrees of freedom. We can achieve this transformation toward decarbonization even if one of the technologies fails. That might be a part of the solution, but it is important to note that we need a portfolio. We need wind, we need solar, we will still need some fossils during the transition period, but the trend is strongly toward decarbonization in the world. Also in this case, with the nuclear phase out, we still have a phase out of oil. A peak of oil occurs over during this decade. And last, but certainly not least, let me show you an exemplary pathway that we have examined in the flagship report. And Professor in the episode number 2, we'll focus on that quite a lot. Let me just show to you how radical this change would be. In this case, we would have already 50% renewables during the next 20 years and totally renewable energy system by the middle of the century. That's possible. Energy efficiency improvements need to be even larger. We have to save about half of the energy against the baseline, against business as usual alternative. And oil, gas, and coal are essentially phased out by 2050. Technically, we believe this is possible, but it would require major institutional changes and, what's most important, very vigorous investment. I'm highlighting you here this exemplary pathway. It is the same as the one before. I've just cut the time to start in 1970s, going to 2050, and you can see here this transformation from the increase of the fossils to a decline of the fossils and the replacement of the fossils with a wide portfolio of renewable energy technologies, basically meaning that over the next 30 to 40 years, we would have to reinvent the energy system, rebuild it more or less from scratch, but we can use some of the infrastructures, and I think that's a very important thing. And the last thing on the pathways that I would like to indicate to you against the backdrop of the historical development and one of the future scenarios I've shown you before, here is a whole range of scenarios from the literature for the year 2050. I don't want to confuse you with wealth of information, but I just wanted to point out one generic finding. This is common to all of them. You can see that energy demand either increases marginally or declines. This is really important. The second conclusion is that the fossils, black, brown, and yellow curve, they're all generally declines and the role of the renewables increases. That means that all of these scenarios are leading to decarbonization and efficiency improvement. Why? Because these are the scenarios that foresee a future where we stabilize temperature increase to about 2 degrees Celsius by the end of the century, meaning we have to radically change the energy system. So I think this is one of the really robust conclusions that the transformation is absolutely necessary. So let me try to summarize this decarbonization and efficiency story. What are some of the framework preconditions for going that way? As mentioned, vigorous energy improvement is almost a must. That means we have to accelerate the development of renewable energy, make them even more affordable. Nuclear is a very problematic energy source. Phase out, we have recommended the phase out, although we do realize that some countries like China, India, Korea might be relying on nuclear for quite a while, but the idea is that globally we have a transformation toward more benign energy sources. Also, carbon capture and storage, CCS, might be a part of the solution, in particular in the transition period, if we don't trap up fossils fast enough. And last thing I would like to mention is that removal or sequestration of carbon from biomass might be a very important future option because that could generate negative emissions, offsetting if we overshoot the target for emissions reduction. What are the two challenges? Well, urbanization is a big one. 50% of people live already in the cities. That will increase to 70–80% over next decades. And cities account today for almost 80% of global energy and emissions. So it's clear that in the cities we have to do quite a lot, and for that we need infrastructures. But also land use is important. We have to protect the nature and do climate-friendly agriculture, perhaps even have climate-friendly diets, meaning shifting toward vegetarian food, which is much more sustainable than carbon-intensive meat diets. So let me illustrate to you how that carbon story does look like in our transformational pathways and our vision of the future. In this graphic, you can see the history starting from 1900s going to today, with the carbon emissions increasing at about 2% per year continuously. On your right, on top, the dotted line are some of the highest scenarios in the literature, really scary, leading to major climate changes. The other dotted line on the bottom shows transformational change, some of the lowest emission scenarios in the future. And the pathways that I have shown you from our flagship report all fall into this green region. It is challenging from the current perspective. Emissions have to peak within a decade, at most 2 decades from now. They have to decline to maybe 1/2, even more of the current level by the middle of the century. If they don't, if we are late, then we will have to generate so-called negative emissions, and that's carbon sequestration in context of biomass that I've mentioned. A very difficult technology in many ways. So you can see that one of the primary objectives is indeed to decarbonize the system, and efficiency is an important prerequisite for that. What is the other important prerequisite is financing. And I would like to highlight to you now what are the investment requirements. This is a very unique collection of the information. On the bottom, you see the total financing requirement in the world. The first column to your left shows how much money we are investing in research and development in the energy area. About 50 billion worldwide. 1/3 of that is public. 2/3 is from the private sources. What is very depressing is how little is going into research or for access. If you remember how big the problem is, only about 1 billion. Renewables, about 12, efficiency, about 18. That all needs to be ramped up. The next column to your right is the early market formation. This is where we need subsidies to support new technologies. About 150 billion are used for that. Still very little for access, much more for efficiency, but insufficient for efficiency in my view. The next column to your right shows the current investments, a total of 1,250 billion worldwide in energy. Equal amounts go to efficiency and renewables, but still only about 9 billion to access. And then to your far right, you can see what we would need for the transformational pathways that I've shown you. We need to ramp up efficiency investments, renewable investments, but primarily increase access about 4-fold, and that is doable. That is a goal that's doable, that would increase the efficiency and help with decarbonization, meaning that we would need to increase the investments worldwide on the order of about 50% compared to today. I would argue that's doable because that kind of money is flowing today in energy subsidies, many of them working opposite to the transformational change and inhibiting the energy transformation we were talking about. Let me just show you how this might occur. These are so-called experience or learning curves. On the vertical scale here, you have the unit cost, dollars per kilowatt installed. The top curve that smoothly goes down shows you the enormous reduction of cost in the photovoltaic systems, about 30% reduction per doubling of cumulative installed capacity. The green curve that also declines is the offshore wind. There we are quite a long way from major cost reductions. I hope that they will occur. But on the opposite side, you see the red and the blue curve. That's the cost of nuclear going up. This is what we need to avoid with the new technologies. This is why it's important to have the investment and new institutions to arrange timely diffusion. In our flagship report, and Professor Jürgen Schmidt will be talking about that, we conceive exactly that kind of development for the renewable technologies. You can see the cost of solar, of photovoltaic, biomass, and wind all going down and eventually replacing also in economic terms the conventional fossil-based energy systems. So I would like to come to the conclusion of the first part of this lecture and highlight three findings that I would like to share with you. The primary goal is to secure planetary life support systems to this transformation, and for that we need a new social contract. We need a proactive state with improved participation of the civil society at all levels, from local, national, all the way to global, to enhance the cooperation toward this transformation. The proactive state need to set priorities for sustainability, but also guarantee increased participation of the civil society in the decision making. So I would like to thank you very much for your attention. I hope that this was an interesting perspective on the global energy transformation. I have also prepared for you 3 questions that you might do in the exercises, and I will see you again in our interviews. Thank you very much.